This video is provided as a demonstration for the proposed application in the rehabilitation program. The process starts with 3D scanning the body region at which the 3D analysis is taking place. As an example, in order to measure neck posture, movements, and the range of motion, the patient gets 3D scans in the upper body region. The scanning can either be done by the service provider or by the patient's family members if the necessary hardware is available. To be more specific, if patient's smartphone is equipped with the LiDAR sensor, this scan is possible using third-party mobile applications at the comfort of their home. Next, a checkerboard pattern printed and attached on a flat surface is positioned in front of the phone camera, which is going to be used for recording the video of patients' specified movement practices later on. By recording this checkerboard at different angles and distances specified by user interface guide, parameters regarding the focal length and lens distortion of the camera will be calculated by the application. Using the 3D mesh of the patient's body, customized marker fixtures will be made by computer-aided design software such as SolidWorks or Fusion 360. The main purpose of customizing the fixture is to tailor the contact points of the markers to the body curvature of the patient while increasing comfort during the attachment. As you can see, two markers are required for the purpose of neck movement measurements, one on the forehead and the other one on the chest. Removing the patient's body mesh, you can see the negative space provided specifically for the size of the forehead and the shape of the chest accordingly. To secure the markers and make sure they won't slide on the skin, forehead marker is secured using an elastic band and the chest marker is hanged on the neck using a rope. Both fixtures have checkerboard markers glued on, which will get detected later on in the video analysis section. In order to produce the complex and customized marker fixtures, fused decomposition molding technique, also known as FDM 3D printer, is used. For this example specifically, both forehead and the chest fixtures are printed using PLA filaments, which are hard and brittle. Later on, softer filament materials such as PETG can be utilized for a more comfortable wear. When the patients receive the fixtures, with the assist of a family member, they can wear the marker fixtures and do the action specified by the practitioner while the family member captures the video of the action at the correct distance, orientation, and lighting condition. Some assistive information and graphical guidelines can be provided for the camera operator for a better video recording. Thanks to using two markers, movements gets measured relatively. Hence, removing any unwanted factors such as the handshake of the camera person or unwanted effect of the patient's trunk movement on the measurement of the neck. After the recording step, the video gets uploaded into cloud for further processes. We start the analysis by opening up the application and selecting the video. Next, using the recorded video of the big checkerboard pattern, a camera parameter file will be created for the camera and we need to select it to compensate for any lens distortion throughout the video analysis. Loading the camera parameter to the software, we receive a message to proceed to the motion selection tab. Here, we can see the entire human anatomy divided into 4 regions. Clicking on the arm region, 4 options, namely shoulder, elbow, lower arm, and wrist, will appear for selection. In the upper region, we have neck and vertebral column to select, and in the lower body region, we have hip, knee, and ankle joints to select. Since we are measuring the neck movements, we select the upper body region, then neck, and as you can see, there are 4 motions to be selected for the neck. In the marker detection tab, we start by selecting the first and the last frame of analysis, which helps if the beginning and the end of the video taken by the user are not included in the analysis. After selection, there are two ways to start up the marker detection process. In the normal mode, video gets analyzed frame by frame until the last frame, but activating the parallel computation would boost the algorithm to assign video frames to each core of the processor. This is expected to boost the detection process when the cloud computation gets implemented, where processors such as Threadripper and EPYC are in hand with hundreds of cores to be utilized. For the purpose of demonstration, however, I start the detection process in the normal mode and fast forward to the end of the process. When the detection process is completed, the detected checkerboard is marked with the green color and we can proceed to the marker tracking tab. Since the checkerboards are identical, we need to specify the reference or stationary checkerboard and the active checkerboard in one frame to help the software tracking each individually throughout the entire video. So I first click on the reference checkerboard and then on the active one, and as you can see, the assistive graph appears for further data cleaning. Zooming into the raw detected data, you can see some detected or non-detected frames, which we can estimate using linear interpolation. Next, we go to the 3D analysis tab for extracting the 3D information of the detected markers. By clicking the Compute 3D button, a 3D plot of the marker's location and orientation will appear in this graph, and the operator can rotate the view or select different planes by pressing on these buttons. We can go through the video timeline and see markers' behavior, and in case there is a slight tilt or misplacement of the markers, we can adjust them virtually by rotating and orienting them in 3D space. Once satisfied with the alignment, by pressing the Apply Offset button, the offset gets applied throughout the entire video, fixing any misalignment. Next, in the Filter tab, we can see the location and orientation of the marker values in 3D space. And as it's clear, the data comes with some noises that can be filtered using the filter toolbox provided in this tab. Zooming into the region, the blue line shows the location changes along the z-axis, and the white dash line is the calculated filtered data. You can also combine multiple filters in this tab for a better result. I'm going to apply a Gaussian filter on the orientation as well to get it smoother, and then press apply to get the filters applied. Moving on to the last tab, we indicate the location at which we want the result to be saved, and then click on Create Frames for the frame renders to get started. In this video, on the top left, you can see the neck joint movements as anterior-posterior tilt, where the head goes forward and backward, axial rotation, where the neck rotates around the spine or vertebral column, and lateral tilts, where the neck moves left or right. On the top right, the speed of the joint rotation in degrees per second is graphed, and in the center, the actual video with detected markers indicated as well. At the bottom left, the speed of the movement of the markers along each axis and overall is plotted in units of millimeter per second. And finally, on the bottom right, the 3D space of the marker movements are provided. After the rendering process is done, by clicking on the Export Video button, all the rendered frames gets summarized into a video for practitioners to receive. Enjoy the final result.